In this lesson, we're going to look at how the movement of the bar on the rails creates a change in the magnetic flux in the loop generated by the electrical connection between the conducting bar, the rails, and the wire connecting the far end on the left here. So the bar is set into motion in the example we're looking at, which is some initial flick. So you're going to flick the bar to the right to give it some V initial. The B field in this problem is not changing value or direction. The B field in this example is into the paper and remains constant the whole time. That flick to the right is going to take the flux area, and I'll shade it in here and erase it in a moment, but it's going to take this flux area and it's going to get bigger as the bar moves to the right. So let me erase that and we'll go back and talk more about the mathematics of what's going on. So Lenz's law first. Lenz's law says that nature is going to fight the effect that's causing the induced EMF. So the changing magnetic flux is into the paper and it's getting larger into the paper as the bar moves to the right. So nature wants to fight the effect of growing B field into the paper based on the area changing. So that is why the induced current is going to run counterclockwise in this case to make B induced out of the paper because we have increased magnetic flux into the paper by the sliding bar. All right, well, let's get our equation for what is going on here. We need an equation for flux, and then we need to take the derivative of it, just as we did in our last example. So what we have, flux is always B dot n hat dA. Again, in this case, we could have just made it B dot n hat A. B is constant, because we said the external magnetic field is uniform over the area. It comes out. Now, the area is changing as a function of time, but the integral of dA is still just A. And it's negative because we have the cosine of 180. N hat is out of the paper by convention. When you're working within the plane of the page, positive Z hat is out of the paper. The B field in this problem we were given is into the paper, so that's why it's the negative here. The B value is constant. The area is base times height, and the height is L, and the base is changing. That X value is changing as a function of time, so that when we take our flux equation and take the derivative of it with respect to time, we see that we only have X changing with respect to time. B and L are constant, so we get dx dt, which is V. So the induced EMF is BLV. If we were asked to solve for the current, we would apply Ohm's law, V equals IR. So IR equals BLV, so I equals BLV divided by R. Now, the dynamic of the sliding bar is a little more complicated than just what we've talked about so far, because as you can see here in your notes, we have a magnetic force to the left. Where does that magnetic force to the left come from? Well, it comes from IL cross B. So down here, we have IL cross B, and when we do IL, right, so IL cross B into the paper, right-hand rule, that gives a thumb to the left. There's a force to the left acting on this bar that we gave an initial velocity to the right. So that means it's going to be slowing down. It's going to be slowing down according to F equals MA. So we get ILB, right, sine of 90 degrees, because I is in the plane of the page and straight up. Right? B is external, is into the paper, so that's why we get our sine of 90 degrees. And our right-hand rule gives us negative X hat, so we have ILB equals MA. But as I have here in the notes, and please make sure you get it in here, this is not a constant acceleration problem, right? Because we have BLV on R is I. Remember, we said we could use Ohm's law to calculate the I times LB, right? So we have LB here. LB gives us MA. A is not constant because we have a V in our equation, right? So we get B squared, L squared, V on R. I ran out of room to simplify, but basically we have a V in that equation. It is not constant acceleration. So we are going to see how to solve it mathematically on our next page of notes, where we have an example where we're going to look at the actual force acting on the particle and calculate the acceleration and as a function of time and solve it mathematically. So we'll see how that works mathematically on the next page. But please make sure you get full annotations down on here. They call it motional ENF because it's the motion of the bar changing the area that's generating the flux, and it is a common system to look at when analyzing flux.